So now we'll start the Chapter 9 notes. So this is about hypothesis testing with two population means. We're not going to talk about proportions in Chapter 9. So instead, we're just going to focus on sort of the general outline that I gave you in the previous video. First, we'll talk about being able to use the standard normal distribution. So we'll talk about z-testing. So here, the population standard deviations must be known for each of the populations that you're studying. And then we also need our sample sizes to be at least 30, or we need the variables that we're studying to be normally distributed. So it's the same sort of assumption that we've been using so far for ensuring that our sample means end up being normally distributed. And like I mentioned in the previous video, here's what our null and alternative hypotheses are going to look like. So our null hypothesis is just going to be that mu1 is equal to mu2. And then our alternative hypothesis depends on the problem setup, but it's either going to be that we expect that first mean to be bigger than the second mean, or we expect the opposite, or we expect them to just be unequal. And remember that I like to rearrange them. So if you're studying something like this inequality, I would rearrange it so that it looks like this right side instead, just so that we have a constant on the right side. And that gives us a point of reference for our difference between our sample means. So we're going to be studying these inequalities by looking at the difference between x1 bar and x2 bar in our sample means. So the main differences between this section and the previous section are that the standard deviation is going to change and the way that we compute the test value is going to change. And that's just because we're studying a slightly different distribution. The difference between our sample means is distributed a little bit differently than just a single sample mean is distributed. So because we're changing the distribution a little bit, we're going to have to switch how we compute our standard deviation or the standard error and our test value. But other than that, the procedure is exactly the same. So if it would be helpful to you, I would recommend that you just pause the video and pull up the Chapter 8 notes. And then you can just walk through step by step as we go through this example, the procedure that we normally use for hypothesis testing. The only thing that's going to change here is this set of formulas down here. So next, let me point out, I guess, before we start the example, that if the population means are not known, which is usually what's going to happen, then we should just assume for our null hypothesis that those means are equal. So we're going to assume that mu1 minus mu2 is equal to 0, or in other words, mu1 is equal to mu2. So this is basically always going to be the case, because if we knew the population means, then we wouldn't have to be taking this sort of sample. So the population means are likely unknown, and then we're just going to assume that mu1 minus mu2 is equal to 0. In other words, that those two are equal. That will be our null hypothesis. And then if we end up getting a sample that extremely disagrees with this null hypothesis, then we'll reject the null hypothesis. So let's look at example 1. Here it says the average household credit card debt for a recent year was 15,000 something. 3 years earlier, the average credit card debt was 12,000 something. Assume that the population standard deviation was 2880 for the recent year and 2160 for 3 years earlier. Also assume that sample sizes of 225 were used for both of those years. So here we're assuming that we actually know the population standard deviation, but these averages are coming from the samples that we took. So we don't know the actual population averages. We just know that this was the average that we got from one sample of 225 people, and this was the average that we got 3 years earlier for another sample of 225 people. And now it says using alpha equals 0.05, so in other words, a 5% level of significance, we want to test the claim that there's a significant difference between the two means. So let's start by just writing down the null and alternative hypothesis. If you want to write it this way, then that's fine. So you could write the null hypothesis as just that they're equal, and then we're testing whether there's a significant difference. So in this case, we would be happy if mu1 is bigger than or smaller than mu2. So in this case, we're going to have a two-tailed test because we're happy either way. with mu1 being significantly smaller or mu1 being significantly bigger. And remember that normally in this section, what I would do is I would rewrite this so that I rearrange the terms to appear on the left side. So I would write that null hypothesis like that, and similarly the alternative hypothesis would be written as mu1 minus mu2 is not equal to 0. One benefit to writing things this way is that it makes it a little easier to compare this quantity with the quantity that we're actually measuring the distribution of, which is x1 minus x2 bar. So these two end up being very similar quantities in that case, whereas before we rearrange, it's a little unclear what we would be looking at distribution-wise. Okay, so there's our null and alternative hypotheses. Next, we want to state the test type. So I already mentioned it, but because the alternative hypothesis is that these are unequal, this is two-tailed. So this is a two-tailed test. And it says also state the critical values. So this is a z-test with critical values. And remember that here alpha was equal to 0.05, and this is a two-tailed test. So we need to come up with the critical values that correspond to that. Now, maybe let me draw a picture. So remember that when you're talking about the critical values, those are z-values that are the cutoffs for your rejection region. So those are the z-values that live way over here to the right and way over here to the left in this case, because this is a two-tailed test. And these z-values, the two vertical bars here, are going to determine whether we are accepting or rejecting the null hypothesis. If our test value ends up being further, or maybe I should just say more extreme than our critical values, then we would reject the null hypothesis. But if we end up getting sample means that live closer to the origin like this, then that wouldn't be enough evidence for us to reject the null hypothesis. So we're looking for the critical values for a two-tailed test with a 5% level of significance. For that, you can note that if you want a 5% level of significance, then that means that I want these two tails to have 5% of the area between them. So that means that this side would have 2.5% of the area, and this side would have 2.5% of the area. So if you want, you could just look up the z-values using your standard normal distribution table. You could find the z-values that most closely approximate this. But there's a slight shortcut, which is just to pull up your Chapter 8 notes where we already have some of those common critical values. Now remember that in this little table, we had the critical values that had this area to their right. So if I was looking for an area of 2.5% to the right here, then this z-value would be the z-value that has 0.025 area to the right. And therefore I would look here, that means that the corresponding z-value there is 1.96. And because this is symmetric around 0, this other critical z-value that has 2.5% of its area to the left, this z-value would end up being, so maybe I'll say negative z.025. is just the negative of the right critical value. So our two critical values are plus or minus 1.96. And that's also what you would expect up here whenever we look at the critical values for two-tailed tests. It'll be plus or minus that critical z-value with half of the area. So we found our critical values now. We know that it's plus or minus 1.96. So we'll go back to our example. So our two critical values are plus or minus 1.96. And now it says calculate the test value, and then we'll state the result of the claim. So maybe I'll label these critical z-values that we have right here, 1.96 and negative 1.96. So if we get a test value that's more extreme than that, in other words, further away from 0, then we would reject the null hypothesis. And if we end up getting a test value that lives closer to 0 than our rejection or than our critical values, then we would accept the null hypothesis. So now we're going to calculate the test value. To compute the test value, we have the formula up here. So this is our formula for computing the test value. It is a little bit more complicated than the test values previously because we're using a slightly more complicated distribution. But in any case, we'll be following basically the same procedure, so I'll just write down what the test value needs to be. So it'll be x1 bar minus x2 bar minus this difference between means, mu1 minus mu2. Now remember that mu1 minus mu2, this quantity, we're assuming is 0 for the null hypothesis. So this second term, you don't even really need to write the second term in parentheses here, just because mu1 minus mu2 is assumed to be 0 by the null hypothesis. And then our standard deviation for the distribution that we're looking at is the population standard deviation for population 1 squared divided by n1, your sample size for the first group, plus sigma 2 squared divided by n2. And now I think it would be a little disorienting for me to scroll back and forth between these. If you want, you can just pull up the notes so that you have the numbers in front of you, but I'm just going to be copying them down. So the first population mean, or sorry, the first sample mean that we got was 15,675. The sample mean for our second sample was 12,515. So that was the averaged at 3 years ago, 12,515. And then remember that this quantity, mu1 minus mu2, because we're obeying the null hypothesis for now, that's just going to be 0. So that'll be true in all of these problems. That last term is just 0. And then we need to divide by the square root of sigma 1 squared. Sigma 1 was 2880. That's the standard deviation for that first population. So we divide by that squared divided by 225 because that was our sample size. And then we also need to add on sigma 2 squared. Sigma 2 was 2160. So that squared divided by its sample size, which was also 225. So this is the quantity that we get. If you are not super comfortable plugging in expressions like this into your calculator all at once, then I would recommend just evaluating maybe the numerator and denominator separately. And then once you've evaluated those separately, then you can keep evaluating, so then you could compute the quotient. Or if you want to practice plugging this whole thing into your calculator at once, you can try that on your own. I would recommend parenthesizing this numerator just to make sure that the calculator understands what's going on. And you can leave off this 0 term whenever you plug in. So either way, whenever you compute this, you should end up getting that's 13. So you should get 13.16. So this is the test value that we get. And now notice that if we were to write this in terms of the distribution that we're looking at, our critical values were negative 1.96 and a positive 1.96. And 13.16 lives way over here. So 13 is way over to the right. So it definitely lives in our rejection region. In other words, this is sufficiently far away from 0 that we are willing to distrust the null hypothesis, because the null hypothesis thinks that this data is distributed around 0. And because we got such an extreme test statistic, we are willing to reject the null hypothesis. Okay. So I know this video is going to be a little bit long, but I think it'll be best if I just squeeze in example 2 before I conclude. So there's an equivalent way to determine whether we should accept or reject the null hypothesis, and that's by using the confidence intervals strategy that we talked about earlier. This is basically, in some sense, just a rearrangement or sort of an equivalent approach. So these will come up with the same answer, but we can still solve the same problem using confidence intervals. And the formula that you'll need for that is this one. So what this formula is saying is that the actual difference between the population means is going to be trapped between these two extreme values on the left and right side. So that's what we're going to do to determine, well, that's what we're going to use, rather, to determine whether this difference could be 0. So if that difference could be 0, then we would accept the null hypothesis, because the null hypothesis thinks that it's 0. If that difference cannot be 0, statistically, then we would reject the null hypothesis. So if that difference is unlikely to be 0, we would reject the null hypothesis. So now we'll do the same thing, but this time using the confidence interval approach. So I'm just going to plug straight into this formula. So x1 bar is 15,675 minus x2 bar is 12,515. And then we already found that that critical value was 1.96. So I get that times the square root of sigma 1 squared divided by its sample size plus sigma 2 squared divided by its sample size. And now that's supposed to be less than mu1 minus mu2, which is supposed to be less than that difference again. So x1 bar minus x2 bar. I'm going to run out of room. This time plus our critical value, so that would be plus 1.96 times that square rooted expression. And I think I'm just going to put ... under the square root, because it's the same square rooted expression that we have on the left side here. Okay, and now if you evaluate this underlined expression, then what you'll get is a 2689.6. And again, if you want to practice using your calculator to evaluate this all at once, then you're welcome to. Alternatively, just evaluate this piece by piece until you break it down into bite-sized pieces that you can then plug into your calculator all at once. So we get that as our left endpoint for the confidence interval. And then the right endpoint for your confidence interval will end up being 3630.4 if you just evaluate this expression. And now notice that what this is saying is that we are 95% confident that mu1 minus mu2 lives between these two numbers. But these two numbers don't have 0 in between them. So what this is saying is we're pretty sure that the actual difference that we're trying to measure lives between 2689 and 3630. And therefore, this difference could not be 0, or at least is extremely unlikely to be 0. So we would reject the null hypothesis. So these will always come to the same conclusion. This is just an alternative approach here. And there is a shortcut for deciding whether this interval that we're talking about, there is a shortcut for deciding whether this interval that's given by the confidence interval includes 0 or doesn't. So remember that what I was saying is that if 0 is between these two numbers, then the null hypothesis could be true. But if 0 is not between those two numbers, then we would reject the null hypothesis. For 0 to be between those two numbers would have to have opposite signs. So one of them would have to be negative, so that really the left one would have to be negative, and this one would have to be positive. Then 0 would be between those two numbers, because 0 is between any negative and positive number. But if those numbers have the same sign, so if they're both positive or if they're both negative, then 0 is not between those two numbers. And that's what gives us this little shortcut for deciding whether to reject or accept the null hypothesis. It just says if those two ends have opposite signs, then you could not reject the null hypothesis because 0 would be in your confidence interval. But if those two ends have the same sign like they do in this example, then we reject the null hypothesis because we're pretty confident that this number is not equal to 0, and therefore that mu1 is not equal to mu2. So that's actually the end of section 9.1. The last thing that we're going to talk about in this class is section 9.2, which is how to do this whenever you're using the t-distribution instead.